I would argue that high density polyethylene, even the older resins, the 3408, is an amazing material. I benefit as an engineer and designer specifying this material. I have so much more confidence in seeing um, long legs and multi-kilometer long outfalls installed by my mentor 30, 40 years ahead of me that are still functioning as designed.
Greetings, everyone. My name is Peter Dyke, Executive Director of the Alliance for PE Pipe and host of your Poly podcast. I'm excited today to have two of my friends with me, both Richard Kolasa and Dan Landy. Hello, Dan.
Hey, what's going on? I was nervous who you were going to say your friends were for a second. I thought I was going to be left out in the dark.
Well, I try not to let the general public know that we're not friends. We try to keep
three people on the call. Yeah.
Anyway, welcome, Dan. Tell us briefly who you are and what you do.
Yeah, Dan Landy. I handle all the engineering services at the Alliance. So dealing with outreach from contractors, clients, specifiers, really helping people in their adoption and all those questions that come along in their journey to becoming more familiar with polyethylene.
Yeah, Dan Landy, Director of Engineering Services. And you have a team of 4 people. Alan Ambler's the chief, and he's kind of the face of the Alliance's engineering program, but you're the one that gets a lot of that work done, aren't you?
You got it. Yeah, he definitely has the presence with the webinar program that people are most familiar with, and one of the main reasons people keep coming back for more assistance.
Yeah, he's done a great job. And with us is Richard Kolasa. Hello, Richard.
Hey, Peter. How are you doing?
Fantastic. Excited with our first webinar of 2025, and we have a fantastic guest today. Tell us who you are and what you do, Richard Kolasa.
Yeah, I'm the technical sales manager for WL Plastics, basically looking after all engineering aspects for sales, roadblocks, or information spec development. I'm also been a outstanding member of the Hydrostatic Stress Board of PPI, so setting policies and regulations. Adrian, if you need a job or you need a position on a board, you're more than welcome to take mine after 35 years. It was supposed to be a 3-year term, but I don't know. It's my 35th year. But I've learned a lot. I've met a lot of great people, trying to promote, really helping out the Alliance with promoting polyethylene pipe and its advantages and what it can offer to society. That's been quite a challenge for the last 12 years as well. So we've grown, and been a pleasure working with Peter on that aspect. And yeah, it's just anything engineering or helping out Dan or helping out Peter and Adrian. Even I don't know how much we can help out you. You're pretty innovative from what I can see, but I'm looking forward to the podcast.
Yeah, just briefly, Richard, thanks for the introduction. WL Plastics is the largest producer of polyethylene pipe, and you're kind of their lead technical guy, right? But you briefly mentioned the Hydrostatic Stress Board of the Plastics Pipe Institute. How and why should we care about HSB?
Well, we evaluate all of our piping products through policies that we developed over the years, and these policies basically test polyethylene for hydrostatic resistance. So we want to make sure that not only do we have longevity, but we have test methodologies that actually put that product to the test and really try to take it to failure, so we understand how it's going to perform in services without failure. So we take it to failure. So we have lots of different challenges, from composites to PEX and monolayer pipes and everything. So that's really the crux of it. It goes into a lot more detail than that, of course, but really just testing those products to make sure that they perform the way we expect them to perform without failure.
Yeah, so if we say that we have a 100-year life product, the HSB people are responsible for making sure we're not lying.
That's correct. We will have companies come to us with special cases. If they have, let's say they don't meet all the policy requirements, they will come to us and they will ask for kind of a forgiveness aspect, I guess, if you want to call it that, or exception to the policy. And also, we want to just make sure that that 100-year service life is lots of different aspects of that: chlorine resistance, hydrostatic stress resistance, load impact, stress resistance, the whole 9 yards. So it's that whole gamut of how that pipe is installed, and making sure that it last through that expected lifetime.
You know, in many respects, me and the Alliance, we are the voice of the industry from the standpoint of how should municipalities and consulting civils design with polyethylene. And I have been sometimes criticized, Richard, for talking about failure, because nobody wants to talk about failure. They want to talk about how great the product is and what we can do for you. But at the end of the day, it's all about failure, isn't it?
Yeah, I mean, if you can't get a product to fail, then you can't understand what its limitations are. So the extreme testing that we do, like a typical operating system for municipal water might be at an ambient temperature at, let's say 80 PSI. Well, we're testing these products all the way up to 90 Celsius or 180 degrees at 425 PSI with chlorine concentrations and everything to try to make them fail, because they just, they do have longevity associated with them. So with the development of the new products, that was a real challenge for us. Some of the old test methodologies just didn't apply because they just didn't fail. So then we just didn't know how they were going to apply in these under these new circumstances. So
to put it in my words, you took polyethylene to a really high temperature at a high pressure and brought in a chemical to try to make it fail.
Yeah, that's one aspect. Yeah, absolutely. Yeah, and we did. And it's still the test method to establish, in this particular example for chlorine resistance, the CC3 rating. I mean, it's still 7,400 hours that you have to meet. So, you're almost talking 10 months of testing. So it's a long-term test. For establishing hydrostatic design basis, I mean, you're talking about almost a year and a half of testing. And if it doesn't fall within the guidelines, then you have to start again.
Crazy. I feel like, I really want to introduce Adrian, but it's like, I kind of want to keep going on this because, the whole issue of testing and the ability of the pipe, all these other pipe materials tell us how great they are and why they're so much better than polyethylene. But Adrian's not using PVC in the Arctic, yet we use it in our water, it's the pipe in water distribution. Yet we're going to talk today about, putting polyethylene into these crazy situations, Richard, that you haven't tested for, but Adrian sure has. So anyway, let's get to that. Thank you, Richard. Welcome to the podcast yet again. You're a regular visitor here and also been a longtime sponsor. So thank you for that. Adrian Hannam, welcome to the Poly Podcast.
Great. Thanks for inviting me to participate. I wanted to hear more from Richard, actually. This is helpful for me. And both Peter and Dan meeting you last year in Nanaimo and Vancouver Island was helpful. And thank you for supporting me with my challenging questions over the last number of months. I'm originally a mechanical engineer, and out of university, I went to Australia and spent 10 years specializing in marine construction, a lot of it terrestrial, but involving marine access. Upon my return to Canada, I transitioned into from pulling wrenches and being a contractor to now working as a consultant. Much of my work involves the final mile of the water cycle. So a lot of my work is related to niche engineering related to conveyance of water. We're dealing with water from wastewater treatment plants and returning them to the ocean in a manner that met the very challenging regulatory climates here, predominantly in Canada, and meeting the physics of the oceanographic processes that are typical on the BC coast. I've since, over the number of years, transitioned to do more than discharging water. I'm doing a lot of pulling water, intakes, force mains, of course, outfalls. But our work has transitioned at GreatPacific from serving predominantly cities and municipal discharges to that of industrial size discharges, water intakes.
Got it. So you've got a lot of experience. So on those that effluent, so you're taking treated fresh water, sewage, industrial water that's been refined, if you will, or cleaned to a standard and dropping it in the ocean.
Yes. So typically what will happen is there's various regulations that will communicate the requirements for a discharger to meet or renovate their water to a certain standard. And then we will work to return it to the ocean in a manner that causes at least impact to the oceanographic processes, the recreators on the water, and the critters and animals, plants that that live in the water.
Give me a quick review, the logic of, most of these outfalls I've read about and seen pictures of. And, we also met you because of Jeff Lohr. Jeff Lohr from ISCO AH hosted these roadshows, or the roadshow that you attended in Nanaimo, British Columbia. And the images that I've seen and that Jeff has told me about are outfalls that use polyethylene that deliver the water well below the ocean surface or the bay surface. What's the logic behind, why don't you just discharge it at the surface? Why do you bring it below the surface?
The general impetus for discharging at depth is to reduce the potential for human health impact with this water. Even though the water is renovated, there are various chemicals that still remain within the water, and the goal is to try to put it back and diffuse it and mix it. It's essentially our team works as oceanographic bartenders to take certain quantities of water that's renovated to meet the regulatory requirements and discharge at depth while intercepting the prevailing oceanographic currents. So we create mixing, and the whole plan is to try to trap the water from reaching the surface. So coupling the discharge requirements with the actual physics, and then post-construction, then we actually do water sampling to show that we've met those requirements.
Oh, very cool. So do you often work as forgive my language here, but the general engineering consultant, or are you a sub to another consulting engineering entity?
We fit it. We wear various hats. From my prior experience at leading construction teams in remote places, I still do design build work. I typically do that with my industrial clients in the Arctic. But most of our work is predominantly from other engineering firms that recognize us as experts in this niche engineering. And part of the reason is that we own our own vessels, our own ROVs, we have commercial divers in-house. So if someone needed us to go this afternoon, we could go. So wow. It's an atypical model for a consulting firm, but we have a small group of Swiss Army knife type of people who are very capable mariners and scientists, oceanographic experts, marine biologists, as well as civil and mechanical engineers.
When Dan asked me about you, I said, well, I'm not sure if he's an engineer or a contractor or both. So it sounds like you're primarily an engineer, but you self-perform some of your designs.
I do, yes. And so we do support design build construction groups, consortiums that have come in either JV or primed the work and brought us aboard to help essentially ascertain the design metrics or the deployment loads for laying large diameter outfalls, water feed rates, air pressures, tug pulls, tensions and winches and such, as well as designing the weights. But typically my work is supporting much larger firms with the final mile of a water processing system. Typical for a discharge, we would design the outfall, and our drawings would be wrapped into the global project, the drawings and specifications, and then we would be brought on board to oversee the construction and the contractor's ability to make it look like the IFC drawings. And then we'll seal those drawings and make records, close it out, and often support the discharger or the owner of those assets to show that they're meeting the regulatory requirements.
In the opening, Richard and I were talking about failure, and I noticed in your bio on your website, which is like the coolest website I think I've ever seen, you've got you've got like a 5-minute MPEG of some very cool video that you shot on projects. It's like, God, I'm learning right now just looking at your website. But you talk about cyclic and fatigue failure. And, I would think, since we don't suffer from that, we in the polyethylene world, you're talking about legacy materials, but in these extreme conditions that you put polyethylene in Hudson Bay and the Arctic and up in coastal British Columbia, do you see failure of polyethylene pipe, either fatigue or otherwise?
I have benefited from having a very involved mentor who's in his 70s, who's put dozens of these pipes along the BC coast predominantly, that I have been able to participate in either remediating, extending the service life of the asset, or replacing completely. I would argue that high density polyethylene, even the older resins, the 3408, is an amazing material. I benefit as an engineer and designer specifying this material. I have so much more confidence in seeing um, long legs and multi-kilometer long outfalls installed by my mentor 30, 40 years ahead of me that are still functioning as designed. The main challenges I see with high density polyethylene in these environments is the rigors of the marine environment. It's the abrasion from logs, rocks, marine loads, but typically the failure of the assets I design is not related to plastic. It's usually related to the failure of the weighting system, the ballasting system, to keep the pipe stapled to the seabed under the loads that are typical of that site.
So what does a typical concrete weight look like? How heavy is it, and how is it attached to the polyethylene?
Well, it's an interesting. That's a very interesting question. Is I very rarely ever arrive at the weight first. Typically, when I'm designing a weight, it's always trying to look forward. If for example, if I'm putting an outfall in, we are looking forward 40, 50, even up to 70 years on the community size. How much effluent are we going to produce based on the size of the community, and then the pipe is sized. Once we have the diameter, we've got to work backwards to sort a pressure class, because whatever pressure class we drop DR, we lose internal diameter, which drops conveyance capacity. So I'm always trying to put the smallest pipe I possibly can at a community based upon projections of effluent being delivered to wastewater treatment plant as the community grows. And so what then happens is then I have to characterize the site we can lay the pipe once we choose an alignment. And that characterization involves often putting an acoustic Doppler current profiler down there to determine current loads at various locations relative to water depth, and characterizing what the aggregate sediment transport processes, logs, marine activities, industrial or fishing activities. And that then defines what type of weighting regime relative to water depth. And typically the weighting regime evolves relative to the wave current loads and how they apply to this pipe. One of the easiest ways to mitigate wave loads or in the highest energy zones, just near shore, intertidal or shallow subtidal, is we'll trench the pipe into the seabed. But you can imagine with Canadian regulations, there's a lot of work related to environmental impact studies, habitat assessments before you can even put excavators on the beach and trench a pipe in. So the weighting is probably the biggest challenge of my work, not the specifying the plastic pipe.
Got it. So if you put one quick question, Richard, if you put a concrete collar on polyethylene, do you have a gasket between the polyethylene and the concrete?
There are various ways to affix a weight onto a pipe, and I don't know if I answered your prior question adequately. I have designed weights that actually clamp onto the pipe, and I've also designed weights where the weights are sleeved precast elements, which are commercially available off the shelf components, which are precast and cheap and not novel to the pipe iron outfall I'm designing. And I will sleeve them onto the high density polyethylene pipe at regular intervals. And then we use a ligature configuration, which the weight might be locally mobilized, maybe 100 mil, 4 inches, but it's the cheapest balancing system up to probably about a 30, 32 inch HDPE pipe is to use a precast sleeved manhole barrel concrete pipe, something that's cylindrical. And typically for those, what I will use is a non-steel reinforced precast element, but typically we dope them with macro fiber to give a much tougher concrete. It's usually a C1 mix, which is 35 MPa, 5,000 PSI or higher type concrete. But the clamp on weights, I'll offer some guidance to who's ever listened to this. The clamp on weights is something that no one should be doing unless they have a real thorough understanding of the viscoelastic nature of HDPE and the need to repeatedly tension and tighten the pipes before you send them down. Because when you do lay a pipe, you're going to put it through an S, and the inflection zone between the two bend radius is on the S. That's where you can see a weights mobilize, and you can see a cascade where the weights will slide and hit each other. So going back to a prior question, yes, I will often use a gasket to improve the wet coefficient of friction between high density polyethylene and concrete. Sometimes the easier thing is just to use a really rough form face and make a nice smooth contour so you can bite into the pipe. Alternatively, what we're seeing is externally fused flexure strengths upstream, downstream of the weight to resist them.
Oh, cool. Richard Kolasa, I know you had a question. Great response,
Yeah.
Adrian. Thank you.
Yeah. I
Mhm.
was just, I was also curious, like, do you ever calculate the ballast once you get there to be able to lift that pipe out of the water?
Yes, we've done that. We'll get to a point where when we're launching pipe, typically we will set up and build these pipes at a boat ramp, or where we've got a smooth shore that operates almost as a stinger, say off the back of a ship. And we will stage all the materials there and set up the fuse machine and progressively launch into the ocean. If the pipe is small enough, we will put the weights on between the fuse machine and the shore, and we'll chase the tide. So the fuse machine, if it's tracked, it will go up and down with the tide. But once we get to, say, around the 30-inch diameter and above, often what we'll do is we'll put a barge offshore, stage all the weights there, and we'll put in we call it a guillotine, which is it's a weight where we can put a weight underneath in a two-phase weight system, put it under the pipe, lower the upper weight down onto it, and then we'll do up the fasteners on the side, whether it's 1, 2, or whatever the configuration.
Yeah, that's awesome, because I also look at it from a maintenance perspective. I'm sorry, I'm putting my my mic on mute because I have some gardeners that showed up, and I've got blowers and cutters and everything going. I don't know if you guys can hear that in the background or not.
Oh,
If
it's
you
perfect.
can't, oh, that's great. Okay, so that's great. I had so the other aspect of this is, having that dynamic load on that pipe when it's, thinking that you're never going to lift that pipe up. Have you ever pumped that thing full of air to lift that pipe up to do any maintenance or any from corrosion of the concrete or anything like that?
That is an excellent question. When you lay an outfall, ideally, when you're venting air at the offshore end, I don't know about the audience's experience related to laying pipes to the seabed, but typically there's 3 variables we play with when we're laying them, which is water feed rate, it's the offshore tension that we pull by typically a tugboat or a vessel of some kind, and the third is how much air pressure we build at the offshore end of the pipe. So as water comes from shore and it displaces the internal volume of air, which now allows the pipe to sink to the seabed and contour the seabed, which is why high density polyethylene is so great. It'll contour and it'll remedy its own scour processes from current in the water, which is great. But as you're laying, there are times when, for whatever reason, you've got to stop the process. You can actually reverse the process by pumping air back into the offshore end and purging water out the shoreline. In the 13 years I've been doing this, I have not reversed an outfall yet. Other than what I've done in the Arctic, where we've had a client which unfortunately could not strip air from going down from their effluent before it went into the outfall at the shoreline. And what they had done is they had an overweighted piece of pipe near shore. And once the effluent got past that overweighted portion, the overweighted portion would be that if there's air in the pipe, it would not come up. Once effluent with air got past that overweighted portion near shore, all that air coalesced and was not being conveyed to 1.4 kilometers offshore to 150 feet. And it makes a bubble and pulled up to the surface. So 2020, beginning of COVID, we got mobilized to the Arctic to a gold mine, and I brought a dive team up in ROV, and we cut holes in the ice. And the very first hole we found, the pipe was frozen into the bottom of the pack ice. So we had to cut the pipe below the ice, or risk the pack ice pulling there's a DR17 10-inch HDPE outfall with probably several tens of tons of tensile capacity. It could have pulled the sea can with the discharge processing components into the ocean as well. So we were contracted to cut the pipe below the ice, 1.4. That was originally 2.2 kilometer pipe. We cut it 1.4 kilometer out in 60 feet. We came back next summer, and what we typically do is to straighten the pipe, I'll use, say, a Romac Alpha. It's a brand of a coupler which I can cap and cam onto the end of a naked butt end pipe, fill it with air, bring it up to the surface, and we'll pull it straight and then relay it. Speaking to what Peter asked earlier about weights and their mobilization, those precast weights I told you, we used for that project, we used 12-inch internal diameter precast pipes cast in Vancouver, flew 500 of them to the gold mine in the Arctic, slipped them on, that pipe has gone up and down dozens of times. And how I know that is the side scan looking at the seabed. It's a very boring clay bottom there. I can see all these regular intervals of the pipe, dozens and dozens of lift off points at the bottom where they've sent air down and laid back. And those weights never shifted, the weights never failed. So I have so much more faith in HDPE from the cyclic perspective, the tensile capacity, especially when the temperature in August at depth is -2 So it's below 32 Fahrenheit as well. High density polyethylene plays nice even in cold temperatures, innumerable cycles up and down with weights on it. Ideally, we try to avoid that. And we've since avoided that pipe this last summer, and it's a non-issue better now.
So we had an interesting conversation in Hawaii with Mackay Engineering, and they created these models for that dynamic because they had they're actually doing an intake where they dropped off a cliff and they had this thing strapped in with cables. And this, when the currents came in the spring, they said they rotated. And I'm wondering, do you guys have any modeling that you do for those types of fatigue movements?
Well, I'm familiar with some of what Mackay is doing in Hawaii with their OTEC system of pulling deep water from the shore, from the depth. We've participated in a couple feasibility projects for that. My experience and my mentoring and guidance to date has been such where we try to put the pipe onto the seabed and immobilize it, where I understand the reef and seabed structures in Hawaii are a little bit different than what we're playing with in Canada, both Arctic and BC coast. But from my experience with high density polyethylene, all our weighting and internal calculations, we use actually our own internally developed software, which is pretty cool. And every project we do, we use it as an opportunity to calibrate our weighting design. What I have not participated in is trying to deal with, torsional capacity of HDPE or cyclic capacities. Although I do put weights on pipes, particularly at the diffuser, where I underslung the weight like a keel of a sailboat, so I can induce a writing moment. So I keep my diffuser ports, which are typically need to be oriented relative to the seabed, upwards. So I do think torque in high density polyethylene, but not to the extent that Mackay has. And I'd like to participate with them if they were interested.
Yeah, I was well for us. I mean, when I sit on an HSB board and Peter asked me about fatigue failure, and I say, well, we don't fail by fatigue because when we tested it dynamically in pressure tests where we had surge applying to it, it's a little bit different. It's in a hoop stress mode instead of a torsion or a torque mode or a twisting mode or whatever you guys run into. But it's kind of interesting to know, what those limitations are, because we do have a limiting tensile strength and we do have a modulus value for that product. And it's just kind of interesting to see these kind of crazy applications survive, especially when you think about a weight on the end of a pipe and you're torquing in a certain area, and you have all that weight on one side and then you're holding it on the other end, it's probably only a couple of areas that it's taking most of the stress or even the strain of that movement. And I find it fascinating that, you're not seeing the failure occur. And it's just, when we get asked those questions, we have these examples. Well, it kind of makes your head a little bit big and kind of you push us up a little bit to say that, hey, we don't fail by fatigue. And here's an extreme example.
Well, I'm doing a force main. It's a 350 meter long force main at 12 inches. Right now, we're going to try and construct it this summer. I've done a number of these. It's on the west coast of Vancouver Island. And what I understand is that pipe, the reason we're replacing this pipe is the existing force main is a 3408, I think 200 PSI rated pipe. We're getting failures at the butt fusions, which is the typical failure mode I've seen from some of the older pipes where maybe the polyethylene was less capable of tolerating the type of cracks and loads you put in them, coupled with maybe a poor understanding or compliance with the fusion requirements of the era that those pipes were being constructed, probably back in the 70s and 80s.
Yeah. It's 50 years old. And in those 3408s, Adrian, we were saying at the time, you're looking at a 50-year life. so you're at 50 years on those. But I would say that if you're seeing failures at the joint, typically we say that joint is as strong, if not stronger, than the pipe wall itself. The same was true back then. My guess is those fusions, to your point, were not conducted correctly. I do have a question for you. A lot of times, in just run-of-the-mill polyethylene work, Adrian, a civil engineer will say, my municipality is operating at 80 PSI. I'm going to use a DR11, even though that's 120 extra. That's what I'm going to use, DR11. So the standard answer for an engineer in the United States and Canada on a typical water or sewer job is, if there's anything kinky going on, anything that's going to add stress to my pipe, difficult installation, big pressure spikes, I'm going to go with a DR11. I'm going to add wall thickness. Do you use the same logic? Do you like to add wall thickness on your projects in Hudson Bay in the Arctic?
That's a really good question. You can imagine if you look at the hydraulic grade line from my work, you'll find often that I'm almost at end of pressure by the time I'm several kilometers offshore and discharging at depth. So when we specify an outfall, for example, I'm needing ever decreasing amount of pressure class or capacity to discharge the pipe. And what I've seen, let me say it this way. My mentor and the other outfalls that I typically work on are the heritage outfalls I'm replacing or force main, not so much force mains, more outfalls. There was a propensity to specify higher pressure class, lower DR near shore, and the pipe would transition to higher pressure classes or lower pressure capacity as you got up towards the diffuser, because the pipe was working relative to a hydraulic grade line, less pressure.
The higher DR number, excuse me, just to correct, higher DR number, lower pressure class.
Well, lower DR means higher pressure capacity. So a lot of my work, so for example, I will often specify for an intake, I will specify a DR11. And the reason is because I don't need a 202 PSI discharge capacity. I need the external buckling resistance capacity for an intake, so I don't suck at pads. So I use thickness on intake lines for avoiding collapse. And where I deviate from my my mentor and some of the other fellows I've seen previously is the need to have thickness. And so I will drop a DR to say DR11 or DR17 if I've got a really energetic wave zone for smaller diameter pipe. But of course, DR is a ratio of the diameter. So if I'm up at a 32 or 36 inch pipe, I would probably be around a DR21, DR26 pressure class. But what we found is if I only need to be discharging at 40 PSI, I would never put a pipe rated for 40 PSI in, because what ends up happening is if they're going to build a kilometer long pipe and I'm going to pull on it and I need to, the catenary is developed by the water depth and how much weight I need to put on this pipe, the tension loads can spike and you're at the capacity of the tension, capacity of the pipe. So what you'll see is what you've saved in buying plastic, or the owner buying plastic, you've bought in risk from the contractor. So typically transitioning to a thicker wall by lowering DR will allow you to actually reduce risk from the contractor, which will benefit the owner twofold. Their pipe will actually survive the rigors of someone dropping an anchor on it. Higher tension poles, you can go faster. These lays, while they look in a two-dimensional plane when we go through an S, you're actually three-dimensional because you've got currents going up and down the coast. So you can imagine building an outfall for a couple months, a couple kilometers long. When we lay these pipes, we do them in 4 to 6 hours kind of timeline. So it's a bit of a stressful process. And often you need that tugboat to be able to go hard. So thick wall is what I often guide the clients, especially while working beaches and you're looking at 10% gouge concerns. So I hope that answers.
Fascinating. Yeah. What a different way to look at a common issue that we see. Question for you. The last word in your company's name is environment. How does polyethylene play into your enthusiasm for respecting the environment?
Well, I guess what I've had the opportunity to do is see how steel and concrete degrades in marine environments. And typically when we age a pipe or mothball steel pipe, which there's still a bunch of them down there, they're left on the seabed. And it's difficult to recycle those components. So they manifest as an impediment to the seabed for fishing activities, industrial activities, other utilities, and similar. But a lot of the newer pipes that I'm doing, when I specify high density polyethylene and we commission the pipe, I have the ability to go back down and pull the old pipes off the seabed. So we're actually recycling high density polyethylene that's been on the seabed for many years. And it's become a very typical component of our work scopes. So not only am I putting I believe a fairly lean design for our new pipe systems we put into the water, whether they're an intake, outfall, force main. High density polyethylene permits me to go and pull the old pieces of infrastructure out and recycle them, keep the seabed clean, and also if you don't do that, there's a chance you'll end up seeing the weights fail and the pipe coming up on its own because it's buoyant. And we've had a number of those projects. Usually they're exciting and involve an emergency. So that's where we try to pull them out in a controlled manner after we commission a new pipe.
You know, Dan and Richard talk to me a lot, and, you know, I'm not an engineer, so I don't necessarily understand this like you guys do, but they talk about the need to remove air, Adrian, from these pipes. And I recall you and I were talking yesterday in brief preparation for this call that entrained air is a significant issue for you. And the fact that polyethylene, you know, is leak free and it doesn't have air entering it or exiting it, you have to plan for that. To help us understand, you know, the worst case, what happens when air gets entrained and how you manage for it in the design process.
There's a number of ways of managing it. When we're trying to work with a new client or tackle a discharge project in particular, or even a force main, the force mains are less of an issue for air, often because we're working in full pipe flow through the conveyance system. The challenge for us is with discharge systems. So you're running down a hill from a treatment plant or whatever, that pipe will flow typically an open channel flow like a water slide. And what happens is these long outfalls into the ocean end up being like they're a restriction, they're an exhaust system. You'll end up getting what's called a hydraulic jump, where the pipe will transition inside from open channel flow to full pipe flow. It's very turbid in that location. Depending on your pipe grade and flow rate, you can then convey those bubbles into the ocean. And if you don't have the ability to manage your batching, your discharge flow rate, or purge that air, strip it from the effluent, you can send air down the outfall. Some of the typical symptoms you could result in is if you have a reverse grade, you capture air there and you float the pipe to the surface. So it becomes a navigational risk, destabilize your outfall, but it also can manifest as a hydraulic block or an airlock to your discharge system. So you'll see you won't be able to discharge. So we often get emergency phone calls related to the non-stripping of air, the deballasting or airlocking outfalls. One way to mitigate that would be to strip the air from the beginning or overweight your pipe all the way to the terminus so that you can convey effluent and air. And I weighted a 1.4 kilometer long 10-inch outfall this last summer in the Arctic to immunize it from air discharge.
What does overweight a pipe mean?
So to get a pipe down, I can't sink a high density polyethylene pipe without external or some type of ballasting on it. Right. So, for example, I will typically, if the wave loads or the oceanographic processes are too great for what the pipe can support when it's full of air, put weights on it. If it's going to sink below the surface, that does nobody any surface. So I've got to put weighting on it at just enough ballasting so that the pipe's still buoyant when there's air inside it. I lay it to the seabed. And if now I'm trying to immunize it from conveying air down the pipe, which could lift it back off the surface. Now I've got to, once the pipe's on bottom, I've got to put additional weight on it. And that's something we try to avoid. Another way to mitigate that would be to cut a trench, put the pipe in it, and backfill it. But that's often even more arduous from a permitting and engineering construction perspective.
Adrian, would pigging help push that air out, or is it just because that flow that flow can't exceed, you can't get the pig to go through because of that flow resistance of the hydraulics on the other side of the pipe. And
You can pig it. I have very minimal experience with pigging outfalls, and part of the reason is because of the guidance offered to me by my mentor. There's been various outfall projects on the BC coast where the outfalls were fouled by trying to set a pig down, and then you don't know where the pig is in the pipe. And also, if you have a multi-port diffuser where the pipe steps down in diameter, you can't get your pig to the end flange. So you've got to maintain the same internal diameter all the way. So there's a number of steel outfalls in the BC coast, some in Victoria, which actually have a pig catcher and launcher. But the logistics of trying to get a foam pig into a pipe in 10 meters of water, stick it in a pipe, and then send it a couple kilometers and get it back out are phenomenal. The one particular project in the Arctic that I was involved in, I mentioned several times, one of the main reasons that pipe came off the seabed was because they pigged the 6-kilometer overland conveyance from the pump station to the shoreline and did not push the air out before it went in the outfall. So the reason that whole pipe was sent to the surface is because they pigged from the upland to the shoreline, not realizing that the air was going offshore, and they slowed the whole outfall up to the pack ice. And the unfortunate thing was it floated the whole diffuser up 2.2 kilometers out from 150 feet. It purged all the air, lost its air. Once it purged, it debalanced up and went back to the seabed in a jumble. And so we had to go cut that off. So we try to avoid pigging if we can. But my guidance to anyone who wants to play in this game would be research Foley. Foley is a French engineer who researched aerodynamic discharge systems. They can communicate the variables related to pipe slope and volumetric discharge relative diameter.
F-A-L-Y-E-V-E-Y?
F-A-L-V-E-Y.
Got it.
Okay.
Yeah.
I got it. Okay, thank you.
Yeah, you bet.
Hey, we've got a few minutes left, but Adrian, you told me you had some videos you wanted to share and maybe give a description of what the heck is going on. I've got sharing enabled, so why don't you call a video up and let's talk about it.
Sure thing. So this is that 10-inch pipe from the Arctic. It you can see how flexible it was even before we got it down under the seabed.
Yeah, there's some fatigue on the shore there. So is that full of air or?
That's full of air.
Okay, and those they look like those are the collars, the cement collars you were talking about before, and then you have them. It looks like on the bottom there you have that marine rope or whatever you want to call it, that fiber to hold those in place. Is that correct?
You are correct. So those are 12-inch precast concrete pipe. It's a C14, which is a -3, which is non-steel reinforced concrete pipe, but we've doped it with a macro fiber with the precast out of Vancouver. And then the pipe weights are put on at regular intervals, so the pipe remains buoyant once full of air. The challenge at this location is that I'm standing at our launch location where Fusion launching the pipe, but the seas are too rough for us to go to shift the anchors and slide more pipe out. So it was kind of a lost day, but what it did is give an opportunity to share what we see at this pipe even before this pipe went down.
Yeah, it almost looks like there's a Fusion right at that bend point off the shore there too, which is amazing. So I don't know. Those fatigue, they kind of freak me out as a pipe manufacturer. I'll be honest with you, but because you have no experience with it, right? So it's I'm like this that it's going to work, right? But obviously there's some definite performance benefits there for.
Well, that's why Adrian was saying, Richard, that the most stressful time is during installation. It's not during operation, right?
Yeah. Yeah. It's pretty cool.
I thought I would share another video. And
yeah, let's do it.
We were asking about the pulling of pipe. Okay, so this is my team. We are straightening an outfall that we brought off the seabed.
Okay.
I'm going to pause it in a sec here. On the bottom left, you're going to see the yellow cap at the end of the pipe.
Yep.
And that's what we use to often raise these pipes. And we're feeding air to it through the air hose on the boat. So I've got an air compressor on it. So this is a pipe we brought off the seabed. It had we're facing south, and in the Arctic, the winds is often coming from the north. So when the pipe came up, when the bay was free of ice, it was curling around to the south. So we floated it, pulled it straight, and we're about to relay it again. So this kind of gives an example of that same pipe that I was showing you previously was getting beat up by the waves.
And this wasn't the one that was stuck to the ice.
This was the one that was stuck to the ice. Yes.
Oh, it was. Okay. All
Yeah.
right. Wow.
And,
You mentioned a while ago that you had a customer who a boat had an anchor and the anchor took out the polyethylene. What happened with that one?
well, actually, here, if you look at the screen, this is the same pipe. So we splashed the ROV through the ice. We're going to swim over and we're going to find this. But this is the pipe floating up to the underside of the pack ice, and you can see it transitioning to the left. That's actually back towards shore. But
cool.
if you look at the bottoms of the ice,
Oh,
you can see the recess that the
Yeah.
the pipe made in the bottom of the ice. So this was something we had to remedy quite quickly. But this was a couple kilometers long of a pipe stuck to the ice. So this is the same pipe that unfortunately this last summer, after we got it back to the seabed and overweighted this pipe down to the seabed, the fuel ship that came to site to service the mine and bring in the fuel, unfortunately laid its mooring across the pipe. So it just speaks to the need to, if you put a pipe on the into the ocean, that you work with the regulators and the hydrographic service so you can chart your pipe onto the seabed so that professional mariners at least know what's there. But that gives you an example of one of these precast concrete pipes on the seabed there.
So that's kind of interesting because you said you didn't have metal in the ballast, right? In the collars. So how do you trace it?
How do I trace the pipe?
Yeah.
I use side scan sonar. So one of the pieces of software we use is something called Reef Master, and Reef Master permits me to, once I lay a pipe on the seabed, I can then survey the pipe from the surface and see the pipe on the seabed. There's very rarely linear objects that are not anthropogenic on the seabed, so it becomes easiest way for me to follow these pipes. I'm going to try to share a screen with you to give you an example
Yeah, I was gonna say.
of that. Yeah, it's interesting at this site we have an intake also out in the bay, and we brought divers up to clean the screens, and all the intake screens were covered with jellyfish. So
How deep is that ice? Is that are you able to access that from the surface, or is it?
Yeah, the ice was, I think, at this location out in the bay was about, I think it was 14 to 16 inches thick. It's saltwater ice. At the some of the ponds inshore south from the bay, the ice would get over 2 meters thick, but it's fresh water. And so this is an example I'm going to share with you now. All right, so what this is, if you look on the left, you can see my vessel going along. Okay, so you see that as I progress, this is a berm here on the side, on the down view, and there's two pipes running off. The one pipe to the right of the intake, and then the other is the outfall. So as we go along, I can follow the pipe, and this is how I do record surveys of an outfall after I put it on the seabed. So as we go out, all of a sudden we're into the zone where this is where the ship's anchor was dragged across the pipe.
Oh, that's wild.
You can see the anchor, and then it went backwards, and you can see how the pipe's got a deviation. So this pipe was strong enough to survive ship's anchor getting dragged over it. So I went up, I drove the client's ROV, and the pipe was fine. Knocked a couple weights off that we had overweighted in that zone, which we'll fix this next summer. But I'm very surprised that the pipe was not damaged, and I got much more faith in this pipe even more now.
So
what's that? What?
Go ahead, Richard.
You saw the pipe there, so that was probably before you straightened it, correct? Because at the end where the berm was, that's where it kind of looped around there. Is that what so that was prior to straightening, right? Or re-straightening?
Yeah, so we straightened the pipe, overweighted the pipe. So those videos, and then this side scan I just showed you was after we had straightened the pipe, which is really unfortunate. Yeah.
Yeah. Wow. And then
sorry, go ahead.
What is the big line in the center? What, like?
Oh, the line in the center is the center line of the boat. So the side scan, it's almost like if you took a piece of paper and then folded it into a W, and then we open it. So the center is what's directly below the boat. I can only see that channel and that channel. Actually, I actually have 3 transducers on our unit, so I have a down center channel, but I turn that channel off for what I was showing you. But depending on what I'm looking at, I'll use my center channel and my right channel. But typically, long assets, I just will shift the boat lateral to it and just parallel it. And,
Nice.
In your recent posts in social media from December, you talk about like one was a 1,400 meter outfall. When you talk in terms of outfalls and you say it's a 1,400 meter outfall, how much of that's on land and how much of it's in the water?
Pretty much 1,400 meters. Big outfall. I'll give you an example. Okay, I'm pulling up a video now and I'll share it with you. So I did a pipe up northern BC coast this last year, and here is the video. So I'm positioned on the tugboat. This pipe is 980 meters long. So in this case, I was not specifying the tow force on the pipe, but I'm the designer. This has a 5 ports on it. You can see here where I'm going to come in a little bit closer. Those risers are the multi-port diffuser. As we're running shore, speed up a little bit. So I'm flying the drone from the tugboat. And what you can see is the pipe is not visible inshore of the workboat because it's already on the bottom. And at the shoreline, the pipe will be contoured to the seabed, and where that workboat is where the pipe will be going through the S as we're progressively laying it. So at the offshore end, we're holding air pressure as we're pumping water into the shore. But this gives you an example. This is also a 10-inch outfall for a fishing community in northern BC.
Got it. So that one has the concrete collars on it. It's got diffusers at 12 o'clock on the pipe. And the S you're talking about is a vertical profile as it's descending to the bottom of the bay. That's correct.
Yeah.
Okay.
I've got another example I can share for you. This is a 36-inch diameter outfall. I designed these weights too. So these weights each were 2.5 ton, and they varied in spacing from 4.2 meters to 6.2 meters, depending on the energy that we're trying to mitigate. So I did this, I think, 2 years ago. This is an 800-meter string, and we intercepted, or we basically tied the pipe in where the crane is at the inshore barge with a spool piece and a temporary steel spool piece to allow the sinking to occur. Once the pipe was on bottom, we went in, lifted the spool piece out, and then put in a high-density polyethylene with 2 sets of flanges out of side, a single weight. So this is a common large diameter outfall lay process. This is central BC coast. This is a municipal wastewater outfall. And for this one, I was working on behalf of the Construction Court Consortium, where I designed the weights, contradicted the engineering of the owner because there were some issues. The owner had contracted an engineering team who had proposed laying this pipe by using airbags and deflating airbags off of each weight. It's extremely dangerous to do that because of Boyle's law. Every 10 meters you drop, you'll half your volume of your air. So if you intended to lay this pipe how the owner's engineer had mandated, it's feasible they would have had a dynamic runaway, and the pipe would have just laid itself and potentially then damaged the HDPE pipe because it would have happened too fast. So on this particular project, I designed the weights, the weighting, spacing, water feed rate, tension pull between the barge and the barge and the pipe, and also the tension between the tug and the barge, which is actually not the same tension. So this was a little bit more of a stressful job, but one I'm very proud of. Was how it went.
Yeah. What's the largest? That is very cool. And to bring these videos to it too is very fun. And I'm sorry for those listening. Check this out on YouTube because we'll have these videos spliced into our conversation. So given your experience, I got two questions left for you and we need to wrap up. What's the largest diameter poly job you've worked on? Diameter, regardless of DR.
Probably the biggest that I participated some degree of engineering on was a 54 inch. The one that I've probably carried the most design would be this one, a 36 inch. The biggest pipe we've inspected was I think the largest solid wall high density polyethylene pipe on the coast of North America is in the McLaughlin Point outfall, Victoria. And it's a 2.2 meter diameter. I can't remember DR. I think it might be DR 26. That was installed about 4 or 5 years ago.
Yeah, Jeff Lohr worked on that one too, right?
Yeah, that was a very interesting project. I was involved with bidding an alternative to that project in 2013. And at the time, I think the large diameter pipe we could get in North America was about 1.6 meter diameter. And we were actually looking at bringing pipes from Norway in 250 meter pieces behind a tugboat through the Panama Canal, and then building the 2 kilometer long outfall with 7 fusions. But unfortunately, our team, which was bidding the outfall, harbor crossing, and the whole wastewater treatment plant, which is about $1 billion project, our outfall engineering did not shine relative to the global project. We were unsuccessful. So,
well, we're now making, with Agro down in South Carolina, they're making double XL pipe. I think they're up to 3 meter diameter now, Adrian, pressure pipe. And Dan and I are familiar with, we presented at Showcase this year, 2 54 inch DR11 jobs. So now we're doing DR11 at 54 inch, which is super exciting. And Agro is pioneering that. And I saw when I visited their facility last year, Adrian, I saw a 6 inch wall thickness, 63 inch DR11. So they are pushing the boundaries. Before we close, I have one final question, which I've been dying to ask. You operate at the end of the spectrum. I mean, you're way out there with what you're doing to polyethylene. And we're very proud of the fact that you're able to do this. And thank you for developing your expertise to be that guy. What advice do you have for an engineer who's just designing a routine water distribution or, say, a larger diameter transmission line that really doesn't have much experience with polyethylene? What is it that you know now that you wish you knew as a younger Adrian?
I would endeavor to go find people who have done this before. Benefit from some of the people who have had their knuckles wrapped or earned some gray hairs on these projects. See what does not work. Ask the questions. And that's what I've really benefited from is seeking organizations such as yourself and PPI who can support me and fill in the blanks, but standing on the shoulders of the people who come before you, especially on these long infrastructure projects that I particularly participate in. You make a poor decision, you're stuck with it the whole way along the project. So as much as I try to put as minimal plastic in the ground with my projects, I think it's a safer approach. Municipal engineering on land, you might be able to benefit from a little bit more lean engineering and taking it back to using tables and charts, but benefit from the experience of what did not work. And I think get in the ditch, watch the contractors, talk to the people who are building it, pulling the wrenches, learn what you need to do in terms of tooling, what's feasible, participate in these types of opportunities will make you a better engineer and value add to your owner, the infrastructure you're designing.
Great advice. I'd like to invite you and Jeff Lohr from ISCO AH down to Tampa in December for Showcase, because we'd love to hear you speak to our industry about some of your experience and what you can do with polyethylene. So if you're looking for a trip to Florida, Dan said that he would make sure that your expenses were paid. We would love to have you come down to Showcase in Tampa. But with that, Adrian, any final words?
I really appreciate you supporting me through the various questions and the presentations you made available to me and my group. I link my juniors to your podcasts, and we have a good number of participation, and I endeavor to participate more. I really appreciate you. You look at my work and see that I'm doing something novel and value adding to the industry and this particular product. Thanks for letting me participate and thinking I'm doing a good job.
Oh, no, for sure.
Proud of that. Thank you.
And to think, Adrian, that now you're using a product that lasts decades longer than previous materials, the service level to the owners is so much greater than it used to be because of this great product that it's just an honor to be able to showcase it on the podcast. Wouldn't you say, Richard?
Oh, absolutely. I mean, I was on another meeting yesterday with the building construction division of PPI, and just, what they're trying to do with geothermal, and all the stuff there, and to put, radiators and transitions in the water like you're doing is going to become a big thing, because heat pumps are so much more efficient, and just everything that's going on. I mean, Adrian, I don't know if you know this, but we've gone through a lot of struggles to break back into these markets and try to explain, the performance of this product. And I believe that some of the engineers really don't believe that it can do what it can do. And it's just, I think, from an understanding, like you said, of the product itself is key. Knowing that other people have had experiences with it, and knowing that they've had success with it as well. A lot of the testimonials that we've had, they blow me out of the water. I mean, Peter was a big part of that, and obtaining, I've never had a problem with polyethylene, in gas or water or sewer. It's great, but yet there's still reluctance. But when you see really extreme conditions like yours, it's hard not to take a second look at it, and then maybe promote to take a second look at it. So I congratulate you on your efforts and your challenges that you've overcome. And it's been an amazing experience for me as well.
Yeah.
Well,
go ahead.
Well, I appreciate it. I'm still learning. I'm getting exposed to more high-density polyethylene materials components than I experienced to date. I learned a lot more about dual containment, high-density polyethylene pipe, and in particular insulated pipe. And that changes the game on how I do my marine work, and especially when you're weighting or ballasting a pipe that also has insulation on it. It fights you trying to go down. And I've had a number of clients not understand even the tagging on insulated pipe, and that they thought the DR was the insulation rating on the insulated high-density polyethylene pipe, not the pressure class. And unfortunately, some poor decisions were made for some vacuum lines. And I had to participate on remedying some intake lines being sucked flat. But, with the understanding of what you can do with a vacuum, I've got some static lift vacuum lines intakes running over 25 feet, which is, getting close to a science experiment. I offer some guidance to my clients, but, it's kind of neat seeing what they're doing with it. And I find the industrials clients are the ones that really push the envelope, and I'm learning the most from right now.
Yeah, well, it sounds like we're going to have to do another podcast. We can bring GF Uricon in here and talk insulated pipe all day. So, with your experience, those guys do a great job. Well, with that, guys, we need to wrap it up. I want to apologize to my audience who are used to podcasts that last less than an hour, but I've got to tell you, Adrian, it was well worth running a little bit long today. So thank you for that. So with no further ado, Peter Dyke, the Alliance for PE Pipe. This is the Poly Podcast. And my thanks to Adrian Hannam, professional engineer from GreatPacific Consulting. Fantastic job. Keep up the good work, and I hope to see you at Showcase this December. With that, let's sign off. Catch you on the other side.
Bye.